expressed, fast the particle ratio gets fixed, you get a chemical freezer temperature. From there I want to extract some parameter, I call it compressibility. Then we have the momentum gets fixed, then we get a isothermal compressibility and specific heat and compressibility. So I will talk about that. So temperature as a function of beam energy, you have this is the chemical temperature, this is the kinetic freezer temperature. So John Clemens, who is not anymore, he passed away last year, and he did an enormous amount of work on this in this regard. So I want to talk about two topics next. One is how to get isothermal compressibility, specific heat. So what is isothermal compressibility? Isothermal compressibility expresses how a system's volume responds to change in the applied pressure. You are applying pressure. This is Argo, my former student, and I asked him to pose how you are applying pressure, how the volume is changing. So Kt, the compressibility is -1/V, del P by del P. Negative sign, why negative sign is there? Please think about and tell me during coffee break. And then this Kt is very important, and it has a interesting behavior at critical point. So we can explore this isothermal compressibility, how to understand the phase transition. Now, our friend Stanislaw Markowski from Poland, in 1997 he came up with an idea that Kt can be calculated from multiplicity distribution. Simple multiplicity distribution you make as a function of centrality. You get the mean, you get the distribution sigma. From there, we can get this is the formula Kt equal to sigma square by n V by Kpt. Kb is the Boltzmann constant. We take which we take it to be 1, and we can do that. So then we followed up with another physics letters saying that yes, it can be done. So we showed that we made this plot, Kt as a function of collision energy. We showed that this is a calculation from a simple Hadron gas model calculation, Hadron resonance gas model calculation. It has a nice drop as a function of beam energy. This is what we wanted to see, but the RIG and LSC data, RIG data is not yet properly analyzed. We have very large error bar. What we did, we analyzed the LSC data recently, we published recently, and we have the n, we have the width, we have the mean, we have the width, we have the sigma square by mean. And main thing is, I want to get into details, main thing how to get the background of the calculation. But if you understand the background, we get a Kt of 27 Q by GeV, which is similar to what is calculated from Hadron resonance gas model. There are more different caveats which I don't want to bore you with. But this is an interesting topic, and we are exploring in RIG energy now. So hopefully we'll be able to get a nice phase transition plot like this very soon, in a couple of years. But our data, actually the LSC data is somewhere here. Now, another topic is heat capacity. We have compressibility, then the heat capacity. Heat capacity is a response function which expresses how much a system's temperature changes when heat is transferred to it. You give some heat, like delta E, energy, how much the temperature changes, that is the heat capacity. So this is another of my former student, Nihar. We are in China just before the pandemic, we are in Wuhan, we are eating from the same hot pot. I am using a wood stick, he is using a metallic spatula. You can imagine, this is boiling temperature, the wood has some heat capacity, and also the metal has some heat capacity. So I am okay, I was okay with eating, but he is having trouble because he is using a metallic one. So this is the heat capacity, you can understand. So from there we want to get the heat capacity. So there is a beautiful work by Stodolsky and Surya, which was shown in the physics letter 98, and we extended this work to see if we can get a heat capacity from our calculations. 1/c delta T square by T. Simple. The heat capacity C equal to fluctuation in temperature by temperature. Now we don't have a fluctuation in temperature, we have fluctuation transverse momentum. We translated transverse momentum fluctuation to temperature fluctuation. Let me show you this. This is the published results from STAR PT distribution. We went from PT to temperature, and once I have that, I have the mean, we have the width, and we can get a specific heat. So this is what we did. There are a lot of involved formula, and then it needs a temperature. This temperature is actually the kinetic temperature. we put in a kinetic temperature, and we assume that the fluctuation in the temperature is low, which is probably around, not the fluctuation in temperature, fluctuation in the radial flow is low, which may be a wrong assumption, but nevertheless, we get a nice characteristic for behavior like that. At the phase tension point, everything drops and then becomes flat. This is a HRG calculation. There are some data. There is a good group from China also gave some model. We use their model, so we get a specific heat as a function of M energy. Now, both in LHC and RIC, we are trying to now, we have students now in place to work on these topics, two topics. So, I just want to show you another thing. Recently there is a lecture paper from Alitro et al. We know Alitro very well. They talk about mean PT as a function of temperature. They take our data from ALICE and they try to get entropy. They try to get the degrees of freedom, which I showed you in the beginning. G equal to 3 for pions, G equal to 30 or 40 for quark plasma. From there, using their model in the lecture paper, they get a G equal to 30. So from there, they also get entropy density 14, entropy S by T cube. So very beautiful word towards thermodynamics. And this, using that, we can compare the lattice data, which I showed to their data. It's not very off. It's quite interesting, which we have measured, and they used our data to get the speed of sound. In fact, to get the speed of sound is 0.24 we reported. They have another recent work which goes to transverse momentum correlators. This is what is very strongly pursued in ALICE and STAR experiments. We have the mean PT, and we have like PT, lot that, the correlation. You have when you look at fluctuation, you are looking at mean and sigma. You are looking at correlation, you are looking at the two different phases, how they talk to each other. We use quite a bit of these correlators to get thermodynamics. I have just skipped most of it because otherwise I'll be running out of time. There are very beautiful work on PT fluctuations and correlations to get to different physics. Let me skip. So then Sergei Volosin contributed recently talking about the flow fluctuation, radial flow fluctuation, which we ignored normally. How it is, how we can calculate and get it. So this is what we are planning to do. Now, towards, I don't know, I didn't keep track of time. I'm okay, and 5 minutes. Okay, good. I come back to what was shown by Professor Sulisakar earlier. Fluctuations in the little band. That is my topic, thermodynamics and fluctuation. How do you explore thermodynamic response functions? You have to invoke something. So fluctuation or correlations is the best measure to invoke thermodynamics. This is the picture which I showed in the beginning, which was shown in the morning. WMAP, temperature fluctuation. In heavy ion collision, these are theoretical model calculations from many different models coming from Macrocosmos group, Brookhaven group, and many different hydro calculations. I'll show something. And these are the imprints from the early heavy ion collision early stages. And we are trying to see if we can, in fact, I took one of the students with Basu, trying to see if we spend 2 years, if I can make a correspondence to these two. And there are some papers, not many. Maybe I should discuss with Professor Sarkar and others just to see how we can make a good correspondence to that. And also Surya talked about a little bit of that flow moments from here, the higher moments, higher harmonics of this one. So we try to make a map. First thing, if you want to study this, you have to make a map. Once you make a map, then try to see what happens. So we try to see if you can make a map with so Rupa Chatterjee, who is at ACC, and she had some hydro calculations when she came back from Yavaskala. So we used her hydro calculations just to make pictures like this, just pictures which I saw here in a different way. On the upper level, I have energy density, and below we have temperature. Energy density and temperature as a function of time. Along the x-axis I have time. So this is at very early time, the 0.1 for me, very early after the collision. Then time goes on, this is around freeze out, 12 for me, around freeze out time. So early times, you have the energy density, and this z-axis, z-axis energy density. This is the xy transverse plane. And if I make a binning, you see this is about 200 GeV per cube. Very, very high, and this is about 20. Very big bin-to-bin fluctuations. As time goes on, the 200 goes down to 15 to 4 to 0.6. So Berken energy density, which Berken's formula we calculate, I skip that. That we get out 15, 20, something like that. That's maybe not the very early on, so maybe a little bit beyond, maybe around 2 years or so after the collision. So, but we have access here. How do we go back there? That's the question. And that is very successfully done by CMB analysis, but for us it is not yet done. So I will tell you the difficulties we are having and the success they are having. So you see the temperature is below, you see the red part is very hot, and then the temperature goes down. This blue is the cold part, so cold, it becomes cooler and cooler. If I make a, so as a function of time, there is a huge fluctuation, the fluctuation dies down. Fluctuation, bean to bean fluctuation dies down, becomes close to zero almost. So if I plot energy density and temperature, and that fluctuations, energy density goes down as a function of time, temperature goes down, fluctuation goes down, fluctuation temperature goes down. So this is what we published in one of the archives, not yet published, but it's already quite some time back. So thanks to Rupert, Sumit, we have a nice plot, and this is, now there are many groups working on this kind of studies and theoretical groups, and experimentally it has been picked up. Then we started to look at local fluctuation to make a fluctuation map. And in CMB, the whole sky is free for you. So you can scan one part of the sky today, another tomorrow, another day after. Depends on the data statistics you want. It takes 10 years, 5 years, 7 years, very long time to acquire data. And then once you have the precision of theta phi, the precision of pointing is very high, I think, is extremely high. And then from there you saw this beautiful CMB fluctuation maps. And here what happens, we try to make a bin in eta phi, and then each bin is very difficult to get a temperature because number of particles are only 20, 30, even in the high statistics, high, it has to be done event by event. We cannot do it, we cannot add up. Event by event, it's only 20, 30 particles to extract. We had a way to extract the map, extract the temperature and fluctuation, but the binning is very coarse. We can only do 30, 40, 50 bins, and it's nowhere near to millions of bins which this CMB people have. So there are different ways. Now we are thinking about using PT correlations, transverse momentum correlations to access this map. That work is just starting with, in collaboration with some of my colleagues at CERN. So now this, actually the earliest phase space which we have right now is limited to plus minus 0.9 or plus 1 unit of rapidity. One picture, one new experiment which is coming up in round 5 called Alice 3, which was shown by Federico before, and Jordan also talked about it. And this one, Alice 3 will be very wide in terms of rapidity coverage. We go to plus minus 4, so 8 units of rapidity, we have a large coverage. And so if you have a 8 units of rapidity, instead of 50 or 100 beams, we'll have 1,000 beams at least. So we'll be able to do something. So in round 5, which is from 2032, so this should be online, and with the low PT, these are also low momentum phenomenon. Using the data and also with improved knowledge of analysis, we should be able to get a map. You see, the CMB map is so nice, immediately it captures your mind and you try to look at it. That's what my dream is, to make it so that visually it becomes much more effective. Our event displays are nice, but the event displays are only lines, they are not physics. So this will be physics. So let's see what happens. So my last slide, the Big Bang and the Little Bang. So as I said, Big Bang is one event, one huge event. But we have billions of events in our heavy ion collisions, and we can take advantage of the billions of events. And in the Little Bang, you have things starting and ending up here, Big Bang things starting and ending up here. If you can make a nice correspondence, this will be a huge benefit for our understanding of physics. The CMB has done a lot of physics, as you saw in the morning, but we have not been able to make the map and go down. Hopefully it will be done, we'll be able to do it soon. So, understanding thermodynamics, I touched upon isothermal temperature, isothermal compressibility, specific heat, speed of sound. I didn't have much time to discuss. One can get to shear viscosity eta by S. Barbara talked about it this week. and in very details you are going to discuss the entropy calculations. This is also in the understanding about thermodynamics. Early stages of thermodynamics from delta PT correlation that we are trying to obtain. Higher order cumulants that has been done by our students in India now. PT, higher order fluctuations, effect of radial flow, the local fluctuations getting a map. Hopefully, beam energy scan program and ALICE 3 analyzing this data which is already existing, and future ALICE 3 we should be able to do that. You see, this is Professor Sinha here with ICP QCP conference, exactly thermodynamics with a large number of participants which attended the conference in 2015, ICP QCP. Hopefully, we pick up again in next years. And yeah, so Professor Sinha played a huge role in educating a large number of youngsters, and I am getting old, but there are a lot of students who got really huge boost because of his presence. And also in India, if you look at the outreach, wherever we go, we have thousands of students attending everywhere. Now on Zoom, there's a big thing going on. So all started by Professor Sinha. Thank you, sir, very, very much. And let me stop here with thermodynamics. Thank you.
This talk is open for comments and questions. I can take only 2 of them, please. Yeah?
They are in the behind, students. Okay.
No comment?
Yeah, it's somebody.
Sir, I have a question. Actually, it's a doubt that I'm carrying.
Speak closer so that, yeah.
Hello?
Yeah.
Sir, it's a doubt that I'm carrying actually relating to the class wave model. So, in the class wave model, when we are quoting one phase out temperature, we are basically assuming that all the hadrons got the kinetic phase out, means their momentum distribution froze at the very same instant. So I actually did some little work on the class wave, and this is the confusion that I am having is what is the picture behind this? Because actually if they are elastically scattering among themselves, in reality it should be that different particles will decouple at different time. But when we are quoting one kinetic phase of temperature, we are assuming that they are freezing at the same time, all of them. So, and part 2 of this is that there is a differential fit also. But when we are doing this differential fit as well as this simultaneous fit, we often get temperatures. It's also in your slide, in the first or second slide, the class wave fit, means KT, you get temperatures more than the phase transition temperature. Means you are getting a kinetic phase out at a temperature around 160, 170.
Yeah, there's the interplay of temperature and radial flow. That also makes a difference when you are feeding with the glass wave. But you are right, if when you do pion, kaon, proton different speedy distribution, when you feed it individually, the temperatures are different from the combined feed. And the temperatures could be different, but but this is the best we can do right now. Even the chemical preserved temperature, you can also argue there are a lot of people thinking why the chemical preserved temperature has to be same. But it turns out that the particle ratio which we can feed for pions, kaons, protons and everything feeds to more or less one temperature. So, but there are people who are working on different models, talking about different freeze out scenarios, kaons, proton freezing out fast maybe, or then kaon, then probably pions, like that. But as far as what I saw right now, everything looks like they are fitting. So with the blast wave, why it goes beyond your transition temperature, that I don't know, but that depends on a T and beta.
Yes, so it's the interplay between T and beta, and it is not for even most central. If you look at the plot, it is coming for around peripheral collision. So you are expecting a kinetic freeze out temperature more than the QGP hadron phase transition temperature, and in a peripheral collision. So that is very counterintuitive. That's why it's a doubt that I'm carrying.
Yeah, so I actually don't know, so we can discuss that.
Yeah, so maybe in private.
Yeah, so but this is interesting, good question. Good.
Yeah, Paolo is waiting in somewhere in Germany or wherever. So one more very quick question to comment I can take. As long as the question is short, and answer is even shorter, okay?
All clear?
No?
Yeah. Thank you.
Thank you very much.
Thank you.
Let's talk to my friend